All right, today we are diving deep. We are cracking open the secret code that runs the entire quantum world. It's an equation that completely changed our understanding of reality, and it all comes from one guy, Erwin Schrödinger. So let's get into it.
Look, in the world we see every day, things are pretty straightforward. If you want to know where a baseball's going to land, you just use Newton's laws, right? F equals ma. It's predictable, it's reliable, but when you zoom all the way down to the level of atoms and electrons, Newton's rules they don't work anymore. For that, you need a whole new rulebook. And that rulebook is the Schrödinger equation. It's the quantum version of Newton's laws, but with a huge twist. It doesn't tell you where an electron is. It tells you where it might be. And that difference, well, that changes everything.
So yeah, just like Newton's laws tell planets how to orbit and baseballs how to fly, Schrödinger's equation, which he dropped on the world back in 1926, tells atoms and electrons how to behave. It is, and I mean this literally, a rulebook for how reality works at the tiniest possible scales.
But here's the catch. To actually understand this rulebook, you first have to meet its star player. It's this mysterious concept at the absolute heart of the equation that forces us to rethink what it even means for something to exist in a specific place.
And that central character is called the wave function. You'll see it represented by that Greek letter psi, the one that kind of looks like a trident. The entire point of solving the Schrödinger equation is to find this wave function.
Which, of course, brings us to the biggest question of all. What on earth is this thing? What is this wave function that the whole of quantum mechanics is built around?
Okay, so the wave function isn't a physical wave, like a ripple you'd see in a pond. You can't see it, you can't touch it, it's a purely mathematical idea. And the best way to think about it is exactly what it says on the screen. It's a wave of possibility. It holds all the potential outcomes, all the potential states of a particle, all at once.
And here's where it gets really useful, thanks to a huge breakthrough from a physicist named Max Born. The wave function itself doesn't point to a spot and say, the electron is here. No, instead it's a tool that lets you calculate the odds, the probability, of finding that electron right here versus, say, over there, if you actually decide to look for it.
And this process is almost like a recipe, seriously. Step 1, you solve the Schrödinger equation to get your hands on that wave function psi. Then, Step 2, you do a little bit of math to it. You square its absolute value. All that really does is turn this abstract idea into a concrete positive number we can use. And that number, the result, gives you the probability. Where that number's high, you're very likely to find the particle. Where it's 0, you've got no chance. It'll never be there.
Now this powerful equation doesn't just come in one form. It actually has two main flavors, and each one has a very different job to do. One is all about change, and the other is about stability.
On one hand, you've got the time-dependent equation. Think of this one like a movie. It shows you exactly how that wave of possibility spreads out and changes and evolves through time. On the other hand, you have the time-independent equation. This is much more like a snapshot. It doesn't care about how things change. Its job is to find the stable, unchanging states that a system is even allowed to be in the first place. Physicists call these stationary states. And this is where the real magic starts to happen. Because when we use that snapshot version to find these stable states, we can make some of the most incredibly precise and, frankly, unbelievably weird predictions in the history of science.
Okay, this is the payoff. This is where all this abstract math suddenly spits out concrete answers about reality itself. Answers that just fly in the face of everything we think we know from our everyday lives.
So, let's start with a classic physics problem. It's called the particle in a box. Just imagine we've trapped a single electron, and we're forcing it to only move back and forth along a single line.
Now, in our world, right, a ball trapped in a box could have any amount of energy. You give it a little nudge, it has a little energy. You give it a big shove, it has a lot of energy. There are no forbidden energies. But what happens when we apply the quantum rulebook? What does the Schrödinger equation have to say about this? And here it is. The result is just absolutely mind-bending. The equation spits out an answer that says the electron can only have specific, discrete amounts of energy. It can have the energy of level 1, or level 2, or level 3, but it can never, ever have an energy value somewhere in between. That's what quantized means. Energy comes in distinct packets, or quanta.
And I have to be really clear here. This is not just some quirky math trick. This is a fundamental law of the universe. This idea of quantized energy levels is the reason atoms are stable. It's why they give off specific colors of light. It's the foundation of chemistry. It's how the world actually works.
And it gets even better. When physicists took this equation and applied it to a simple hydrogen atom, the answers it gave were perfect. It not only predicted the exact energy levels of the atom, it also predicted the beautiful, bizarre shapes of the atomic orbitals, those clouds of probability showing where the electron is most likely to be. This was the birth of modern chemistry.
So the equation is an unbelievably successful tool. Its predictions are flawless. But, and this is a huge but, for all of its success, it leaves us with this deep philosophical mystery that physicists are still fighting about 100 years later.
The math works. There's no doubt about it. We can build lasers and microchips and MRI machines with it, but what is the wave function? Is it a real thing that's out there in the world, or is it just a description of what we know, or what we can know about the world?
And the crazy thing is, nobody agrees. The classic Copenhagen interpretation basically says, don't worry about it. The wave function is just a tool for calculating probabilities. It's just information. Then you've got the many worlds interpretation, which says that every single possibility contained in that wave function actually happens, each one in its own separate parallel universe. And there are still others, like Bohmian mechanics, that argue the particle was always in a real spot and the wave is just guiding it along.
Even Schrödinger himself was deeply troubled by his own creation. He called it a catalog of future expectations, which is such a beautiful and honestly, a kind of unsettling way to describe the very fabric of reality.
And that's really where things stand. The Schrödinger equation unlocked the quantum world for us. We are masters at using it. We know how to read the code. We're just still in a massive argument about what the code is actually telling us about existence itself.
So I'll leave you with this final thought to chew on. Is it possible that the solid, definite world we experience is just one outcome from a vast, underlying ocean of pure possibility? Is reality itself just a wave of potential that only snaps into focus when we bother to look at it? Something to think about.